So my name's Chris Dubuque. I'm one of the application engineers with MCAD Technologies. And this morning's webinar, like I mentioned, it's an introduction to SolidWorks Plastics, and it'll give you a good overview about the capabilities that SolidWorks Plastics has as far as injection molding simulation right inside of the SolidWorks environment. Before I get on with the demonstration, I want to make sure that the audio is working correctly. So I'm just going to launch a very quick poll, pretty straightforward as far as the selections are concerned. Either you guys can hear me or you cannot, and that's a good sign. Everybody can hear me. So I got things set up correctly for once. So let's go ahead and jump into SolidWorks and start taking a look right at SolidWorks Plastics. So we're going to use the smoke detector model as our example today for SolidWorks Plastics. And there's a couple things that are really nice about this smoke detector. One, it's something that everybody is very, very familiar with. It's quite recognizable. It's not some obscure random plastic part that we came up with. But on the second side of things is it really showcases, traditional kind of traditional plastic parts. It really has a bit of everything. Obviously the thin walls, the ribs, the clips, draft, some little grating area or grill area, as well as some engraved text on there. So it's kind of a good generic cross-section to take a look at using SolidWorks Plastics. So Plastics is an injection filling simulation software. It is completely integrated inside of the SolidWorks user interface. So the first thing that we need to do is go ahead and add Plastics in from the traditional tools add-ins area. And once Plastics is added into the SolidWorks environment, we'll have a command manager tab just like all of the other functions inside of SolidWorks, which will contain our various commands to set up the analysis, define the mesh, and take a look at the results. There's also a pull-down menu, so if you prefer to use the pull-down menu structure, you can navigate through Plastics in that environment, as well as a full feature manager tree for Plastics functionality. And the tree is really the way that I find Plastics the easiest to use. Now, some of the functionality that I appreciate the most about Plastics is its integration with SolidWorks and its use of configurations. So in this particular part model, it's got several different configurations, and each one of those configurations is a separate plastic setup with its own unique materials, injection parameters, mesh parameters, and also geometry from SolidWorks. So it makes it very easy, I'll say, to compartmentalize things as far as my different studies are concerned. And this allows me to run a number of what-if scenarios simply by switching the configurations inside of SolidWorks. So the first thing we'll do is we're just going to jump over and kind of take a stab at this particular model. Kind of the workflow that we're going to use is we're going to make some guesses, if you will, as far as the geometry in SolidWorks is concerned, as well as the material we select in our injection location over in Plastics, in the hopes that we'll optimize the wall thickness of our part to get a nice complete fill but doesn't take too long to cool. And then we'll take a look at making sure that the quality of that part is acceptable, and we may have to adjust some additional parameters. So we'll get started here by defining the mesh. And the mesh can be defined automatically by the software, or the user can go ahead and manually define it. And that's what I'm going to do in this particular example. Now, depending on the complexity of your part model, whether it's one body like we have up on the screen or multiple solid bodies, the software gives you the choice as far as which body you want to mesh and what do you want those specific mesh parameters to be. So we'll choose the one available mesh cavity, and now we can start defining the mesh itself. And there's an easy-to-use slider bar, and it gives you an estimated number of mesh triangles wherever that slider bar happens to be. And the user can go ahead and define their own value. Now I can intentionally define a very, very coarse mesh because I can take advantage of automatic mesh refinement. And that's what I'm going to go ahead and do in this case. And if I don't like the results that the software automatically refines for me, there is full user-defined mesh refinement on edges, faces, vertices, so you can really get a nice mesh that accurately represents the model geometry. So we'll quickly mesh this with just a simple shell mesh, and it looks like I forgot to turn on the auto refinement, so let's try that one more time. And you can see that the result is quite significant. Plastics is automatically refining the mesh in the areas of small geometries, and I think that'll look pretty good as far as this initial mesh is concerned. Might not be the best, it might not be where I end up, but I have to start somewhere. You can also see a number of tools for editing the mesh. So this is what the software has given me. I can move the triangles around, I can add further refinement, add further nodes, but I really wouldn't do any of that until I get a first pass study, and then I can get an understanding of where I may need to go ahead and refine the mesh. So now that I've defined the shell mesh, you can see a number of additional parameters in the tree. I'm going to go ahead and show the representation on the mesh just so we can see exactly the geometry we'll be working with inside of plastics. Now I just kind of think of the tree as steps 1, 2, 3, 4, etc., etc. So in this case, step 2, let's go ahead and define the material. Now the database inside of plastics has over 4,000 different plastic polymers, ranging from, there you can see ABS, we're up to much more advanced examples, polycarbonates, and the list goes on and on and on, polypropylenes, and continues. So this library, it does come with the software, it is completely user definable, and it's also broken down onto the different manufacturers. So we can sort by plastic company or families, or I can sort by companies. You know, if we use a lot of 3M, or I use a lot of Amoco Chemical, for example, I can get right into their libraries and pull the specific polymer that I want to use. Now in this case, I'm going to switch back over to the family example, and we'll just use the generic polycarbonate as a place to start. A decent material in this case, you know, good material characteristics, good flow characteristics, but I don't know if it's the best material, and that's one of the things that we can use plastics to help determine. Everything about the particular material itself is user definable, so if you need to go in and make changes to all the various curves and data points, you can go ahead and do that. The machine is something else that we can customize. I'm just going to use a default basic machine for the sake of the demonstration, but you can see you've got full control over the filling time, temperatures, injection limits, even getting into the size of the machine and the specific variables about the machine itself. There are several machines that the software comes pre-installed with. Just like the materials, you as the user can go ahead and define and change any parameter that you may need to. But in this case, we're just going to let the software essentially auto-determine the appropriate parameters. The final stage for setting up this initial study is just to define the injection location. For this particular part, I'm just going to make a guess, and let's say we'll put our injection location right on that particular model edge. Maybe it's a good choice, maybe it's a very poor choice. Once again, these are one of the things that we can use SolidWorks Plastics to help us determine. Specify the injection size, 3 millimeter, and we'll add that into the model, and we're done. So very easy to set up. Our shell, our material, changes to our machine, or just choosing our machine out of the library, and our injection location. So let's go ahead and run the study. Now for a simple part like this, the study only takes about a minute or so to run, and it really goes through two different phases of analysis, just a really quick pre-processing phase, and then it will start defining and calculating the results. Now, as soon as the software begins calculating the results, we'll see the various plots and the animations up on the screen. And we can use these initial results to determine whether or not we set things up correctly, or if we already see a problem with our injection location, or if we see something with the SolidWorks geometry that we don't like. And if it continues down, if we think it's going to continue down a bad path, we can stop the study right now, jump back into SolidWorks, start making changes to the geometry, or go back into the setup of our plastic study and change the injection location or the material, for example. So it really gives you a good understanding before the analysis is even finished whether or not it's something that's usable. Now, one thing that I'll point out is it's fairly obvious with this example is racetrack effect or race tracking within the part, and the fact that the mold front or the plastic flow front is rapidly accelerating through the thicker areas of the part, and the thinner areas, as expected, is considerably lagging behind. So this could be something problematic that we can investigate with some of the post-processing results. I'll go ahead and let this finish. Looks like we're about 80% done. And then we can take a look at some of the other post-processing results that plastics gives us. Full fill animations, fill times, cooling times, and a number of other graphical plots and animations that we can take a look at. So it looks like we're almost done here. You can see that for stage 90%, the max injection pressure right around 35 megapascals. So I think we're pretty good. So now that the study has completed, a couple things to point out. One, the results advisor automatically popped up on the right-hand side of the screen to help walk us through the interpretations of the various results inside of plastics, because there are a number of plots. The first thing is just the simple little red light, yellow light, green light. A green light means the part can be successfully filled. And continuing reading the results advisor, max injection pressure, 35.3 megapascals, 5100 psi, but it is less than 66% of the machine's max pressure. So I'll say we're good to go in that regard. There's additional information within the plots. We can continue to read that. You can also see, telling us how to use the fill time plot, make changes to it. But let's go ahead and just take a look at that without going through everything within the results advisor. So the initial plot that we're given inside of plastics is just the fill time animation. And this is going to be the same thing that we saw the simulation advisor, kind of the study advisor when it was solving, show us in time steps. So we can see the flow front move throughout the model. We can see that racetrack effect very obviously, filling the thicker areas of the model before the thinner areas get filled. And we can go ahead and stop it at any time step. I'm going to go ahead and move a couple more and then pause it. And here we can really see that problem. We've almost filled that thick area, and we're not even halfway filled with the thinner areas of that part. And that's going to give us some fairly significant backfilling on those thin ribs across the grills. This particular part's going to take about 2.1 seconds to fill, so really no problem, if you will, filling the part. But let's look at some of the other options within this plot. I mentioned that backfilling, those two flow fronts coming together because of the significant difference in wall thickness. But we don't have to guess about that information. We can turn on the weld line plots and have plastics show us exactly where those two plastic flow fronts come together, as well as the angle, the resulting angle between them. Pretty much every single thin rib on the rectangular and circular grills have these weld lines, and that's something that we will want to address. I think we will need to address. So that's one of the potential problems in the model. The weld line plots can show that to us. But we can also see where the air traps, we can visualize air traps within the part. So this is going to lead us down the path of where we would need to add additional vents. And if we have some significant air trap problems, the air could combust under compression, and we could get burn marks and additional defects on the part. So my guess for the injection location in the geometry was just that. It's a guess. It's a place to start. We have some weld line problems, some potential air trap problems. But let's take a look at some of these other plots before we start hopefully finalizing the design. The pressure at the end of the fill really isn't a problem. Only 35 megapascals, well under the max pressure of the machine. And we can see other temperatures of the actual part itself, central temperature at the end of the fill, average temperature throughout the model at the end of the fill. So a ton of information for all these other post-processing results. One that I'm really concerned with would be sink marks, since I've got this pretty significant difference in wall thickness. So we can graphically see the sink marks throughout the part. Nothing massively significant, but once again, it's all about getting the information back from the geometry, back from the software, so we can start making an informed decision. 2 plots up, the cooling time. This could be very, very significant for the model. And in this case, the cooling time is 62 seconds for the thick walls. And for an injection molding machine, staying static for 62 seconds while the model cools is really a problem. This is a high volume process and a high volume part. We need to do something about that. So we've got some issues with the wall thickness, primarily with this model. So let's go back and start refining the design and coming to hopefully a better conclusion with things. So I'm going to take advantage of configurations, and let's switch over to another example. In this case, we're going to reduce the wall thickness from excessively thick to quite possibly excessively thin. In this case, the wall thickness has been reduced from 5 millimeters in the first example to 1 millimeter in this example. So we're just making a SolidWorks geometry change. Everything in the plastics environment is the same shell mesh, the same plastic polymer, as well as the same injection location. Now, for the sake of time, I've already run all of the other studies previously, so we can take a look at the results. And here we see a very, very big problem. This is a short shot. The model does not completely fill. The fill time is only 1 second, but the part is 100% defective. So we can really finalize and realize that, oops, we made a big mistake. This is one of the big things that would be very, very time-consuming and cost a ton of money if I determined this was a problem after I had the actual tooling built. But now that I've figured out, wall thickness issues right inside of plastics, I can easily go back into SolidWorks and make a change. So 100% defective example here, really no need to look at any of the other results. But once again, because I'm using plastic simulation, I can finalize that. I can figure that out inside of SolidWorks. I don't have to destroy any tooling because I, as the designer, made a big mistake. So let's go to example number 3. As you can see up on the screen, we've increased the wall thickness a little bit more. I'll just use the measurement tool, and there we can see we've increased it up to 2.5 millimeters. So kind of finding a happy medium between extreme case 1 of 5 millimeter wall and extreme case 2 of 1 millimeter wall. Once again, all the parameters for the setup in plastics are the same. So let's take a look at the results. So the fill time isn't drastically different, 2 second or almost 2.1 seconds, so just about the same. Let's take a look at the fill animation. Shouldn't look overly different. We have a little bit more consistent behavior with the wall thicknesses around the outer edges of the part. It isn't racing ahead nearly as bad as the first example. It actually looks like things are coming together fairly uniform across the part. We still have some backfilling around this curved area. We pause it right about there. You can see we're going to have some backfilling in that lower, I'll say, corner of the thin ribs. So I'm imagining if I turn on the weld line plot, we can see that we really didn't fix this particular issue. We fixed some of the race tracking, but we didn't fix the fact that all the thin ribs are backfilling upon one another. And just like the first example, we could go through and look at all of the other plots. Fill pressure, it's actually increased 35 up to 44 to be expected by decreasing the wall thickness, but we got to keep an eye on that. We want to make sure that that doesn't creep up too high. But we're still less than 50% of the injection pressure on the machine. So I'm going to say for now we're probably doing okay. We could look at the same temperature plots and fill plots and things like that. But I'm going to jump right down to cooling time because I expect that changing the wall thickness is going to have a dramatic impact, and sure enough it has. Our cooling time has decreased from 62 seconds in the first iteration to 27 seconds in an actual usable iteration. So we are going in the right direction. We've kind of, I guess I'd say, optimized the wall thickness. At least we're better than where we began. But we still have to deal with all of the backfilling on the ribs and all of the potential weld line defects on that area of the geometry. So the first part of our analysis here, I'd say, is more or less complete, kind of using plastics to dial in the SolidWorks wall thickness to really refine the geometry in order to optimize the filling and making sure that cooling time is acceptable. There are more things that we could do, but I'd say that's a good first example here. So now that we've got the geometry refined, if you will, let's take a look at manipulating some of the parameters just inside of plastics. So maybe the first guess of injecting the part up on this model edge wasn't the best choice. Maybe there are other areas of the part that would fill maybe faster, maybe more complete, and eliminate some of those potential defects. So we'll take a look at the fourth configuration. So we'll go ahead and let plastics load all of its information, and that's exactly what we're doing here. Instead of injecting on the upper edge, we're going to inject in the lower right-hand corner closer to the area that's been the problem with the backfilling, in the hopes that we'll push the plastic from the problem area all the way across those ribs. But once again, this could have impact on injection pressures, could have impact on cooling time, so we'll just have to wait and see. The same mesh, the same machine settings, as well as the same plastic polymer, and we'll take a look at those results. So the graphical plot obviously is going to look a little bit different because we're filling it in quite a different way. But as the animation goes throughout the part, it does look a little bit better. I'm not seeing as much backfilling across these ribs. Actually, most of them look like they're just going across nicely from one side to the next. Fill time is about the same, 2.1 seconds. Let's turn on the weld line plot, and that actually looks much, much better. The circular cutout where the grill ribs go across, there are no weld lines. And then we just have a few weld lines on the rectangular ribs, just 3 pieces of geometry. So considering where we came from, that's a very considerable improvement. Is it the best that we could do? I don't know. That's what running further studies in plastics could help us determine. So that looks pretty good compared to where we came. Injection pressures, they're still creeping up, right around 47 megapascals. Might be something I need to address. Cooling time plots, looking a little bit better, dropped it 1 second down to 26 seconds. So you can really see how to use SolidWorks Plastics, just like the other simulation tools inside of SolidWorks. Because of that tight level integration, it allows you to make these changes effortlessly on the SolidWorks side and very quickly run a new what-if scenario and additional what-if scenarios to help refine the design. But let's say we're not quite done yet. There's still some additional changes that we could potentially make. Maybe we're satisfied with the geometry. Maybe we're now satisfied with the injection location. I could run additional studies, maybe looking at injecting it in 2 different locations or someplace completely differently in the model. But how do I know that that initial polycarbonate material is the best choice for this? Well, in this case, I really don't. I just guessed. Obviously, with your experience on injection molding your parts and what your parts need to be made out of, you'll make a much more informed guess and choice than I did here. But that could be the next stage as far as my design refinement is concerned is going through and looking at material selection choices. In this case, maybe we change it. Instead of using the generic polycarbonate, we use an ABS polycarbonate blend or some of the other, thousands upon thousands of materials inside of plastics. So just like the other examples I've gone through, same mesh, same machine settings, excuse me, as well as the same injection location. But now we can take a look at the flow results. Fill time looks good. I'm really looking at possibly reducing pressures with a different material blend. In this case, drops it by 10 megapascals. But I think by now you're starting to get the idea of how you can use plastics. Looking at that first pass analysis of your part, and then going through the process of really refining everything. Weld lines actually look pretty good. There's only 2 weld lines on the ribs. They look a little bit differently on the thicker areas of the part. May or may not be a problem. Definitely not as significant as the number of weld lines that I had on the initial examples. Now that we've, I'll say, finalized everything in this particular part, we can start talking about, the full scope of the analysis, because at this point we've really only been looking at the fill aspect of it. And one plot that I haven't looked at yet is volumetric shrinkage. So there's really 2 parts of the injection process. One, the plastic filling, but then also the packing of the mold base, keeping the part under pressure while the plastics goes through its phase change from the molten state back into the more solidified state. So what we can take a look at is up to this point are just the flow results, but we can also run a secondary packing analysis, and that's what I've done for this one final example. So hypothetically speaking, if we take this part and inject it and then immediately eject it out of the mold, we're going to see shrinkage of about 11%, which obviously that's going to be very, very problematic and lead to some significant part defects, some warpage, basically a big, big problem. But running this secondary pack analysis allows us to control how long the mold base stays compressed. And it is a secondary pack settings, and we can go ahead and open those there. So we can see additional pressure of 4 seconds based on this profile, and then additional dropping the pressure down to 40% for 10 seconds. So keeping it under pressure based on this particular curve. So let's take a look at those results now. So we can see the pressure at the end of the packing phase, still under pressure, about 15 megapascals. We'll have the same temperature distribution plots, shear stress plots, but what we're really looking at here, just as a comparison to kind of wrap things up, is the drastic difference in shrinkage when we appropriately pack the part, and we can get an idea about how long the overall cycle really needs to be. So in this case, under our 10 seconds of additional mold-based pack analysis, we can see that the shrinkage has been reduced down to a more realistic 3% as opposed to 11% that we saw in that first in a hypothetical example. So you can see over the last 30 minutes, we've really gone through kind of the basic overview of plastics, taking a look at the setup, running through 7 different what-if scenarios to really optimize the geometry, the injection location, as well as making a better choice as far as the material is concerned. The last thing to do for this particular model would go ahead and define a report. Now the report will automatically capture all sorts of information from your analysis, your setup, your material properties, your animations, your plots, and the list goes on and on and on. Now for the sake of time, I've already run the report, so we'll just go ahead and open it up just so you can see what one of these reports looks like. So you can see a number of screen captures. There you can see just the basic smoke alarm cover that I've called it. And then various hyperlinks within the report for the model information, thickness distribution plots, material information, all of the fill time, temperature settings of the analysis, the cooling time, and then the various results. Of course, all of the plots for our materials are defined and given to us. And there we can see the various fill plots. Now, it shows up a little bit strange in Word, but I can go ahead and run that, and it'll actually save the animation as an AVI file and embed that into your plot. So there we can see the results of that animation there, as well as the static plots as well. And this is all information that Plastics has captured automatically. Just a couple of clicks of the mouse, it's all formatted for us, and then we can start making our own, additional conclusions and determinations about the process. So with that, I say thank you very much for joining me this morning with SolidWorks Plastics. If you guys have any questions, feel free to ask. And if you don't have any questions now, but they come up a little bit later, feel free to send an email to support@mcad.com, and we can go ahead and address them. So thank you very much. Have a good day.